Hello students, today I am going to start the topic on adsorption. Okay, adsorption. See here, as per the definition, adsorption is just attachment of all the impurities of the ions onto the surface. Initially, adsorption was used in around 1920 for the removal of the air pollutants by using some chemical liquids. So all those air pollutants, you call it the SPM, RSPM, whatever, they have been sucked and trapped inside a liquid. Okay, so it is a solid particle trapped in a liquid. Now here, in this adsorption process, what is related with the environmental engineering, we are going to do with the removal of any impurity ions like heavy metals or your fluoride, arsenic, mercury, or any impurities like your pesticides in ionic complexes by using an adsorbent. Adsorbent means the material we are making it to remove these compounds. We call it recalcitrant compounds. Okay, so theory you can find in notebooks or other textbook. Say for example, this we call it adsorbent. This solid surface, this is a impurity. This is to be removed. And this one is called adsorbent. And let's imagine from environmental point of view, everything is under the water. These are all water, okay? You call it water or wastewater, whatever. Okay, everything is there. Now, this particle is going to come inside here and it's going to stuck over here. This is called, the process is called adsorption. Now, the main thing that is happening is, the main concept is here, this attraction is due to sometimes van der Waals also. Okay, and sometimes this adsorbent, they have lot of spores inside. So adsorbent number one, surface area is very high. Say for example, if you have a cricket ball, so the surface area of the cricket ball is 4 by 3 pi r cube. But if you cut the cricket ball into half, you'll get 4 pi r cube plus 2 surface of inside. That is pi r square. 2 pi r square you'll get it, right? So the more you break it, the more surface area will be exposed. Similarly, what happened is, inside they have got lot of pores. Say for example, like the mouse used to make burrows, the caves inside the soil. So, but how to make it, that's different. Because of the high surface area, adsorbent are getting attached, sometimes they're getting inside. So I'm not going to cover up much theory part, just a few points. High surface area, and number two, the area is such that sometimes it's called micropore, then mesopores, then macropores. Okay, they have different size area, and one of the best adsorbent is, we call it activated carbon. See here, Why I'm saying active carbon? Because it may be from different type of wood particles, different type of biological materials. If you activate it by at a very high temperature, it creates a lot of pores, and this small body, if you enlarge it, what you will see is you will see a big one, and then inside, because due to the activation, all the organic masses will be burned over here, and inside you'll have lot of spores here, lot of pores. So all the particles are going to get stuck inside. Okay, this is almost a little bit done in BTech. Now I'm going to come for the MTech level. So theory part you can study yourself. Yes, send in the class notes. Now this is the basic fundamental of adsorption. Next one is what are the factors for adsorption. Number one, high surface area, higher will be the adsorption. Temperature also does play a role, but let me tell you that it is not that the increase in temperature will always increase the removal. No. In some adsorbent, the case may be different. But the thing is, the impact of the temperature is going to give either a positive or negative impact. So temperature is somewhat correlated with the adsorption. That's my point. Okay. Another one is pH. Another one is, I'll explain it, initial concentration of the adsorbent. Say for example, if you have a lot of ions, it'll be just like crowded. Very simple example is if you have a lot of fish inside a bucket, the moment you put a hand, you can pluck it out very easily. So overcrowding of the adsorbent itself enhances the removal. Okay. But if you have only one fish in a big tub, it's not that easy for us to catch. So similar concept. And number five is dose of the adsorbent. How much adsorbent? The more dose you use, the more adsorption will be there by default. If you use more chemicals, more microbes will be killed. Similarly, this is the case. Okay. So now let me come to the next step. I have to minimize the use of the green color. This green ink used to get adsorbed onto the white surface very quickly. Now next is classification. Okay. In classification, what we find is there is called physical adsorption. Or we call it physiorption. Number two is, we will be sending you the class notes for this. I don't have to explain the theory. Chemical adsorption. Okay. Or we call it chemisorption. See, whatever the adsorption due to such physical force, this is called physical adsorption. Simple. Okay. For the chemical adsorption, the thing is, sometimes this is your adsorbent. In this adsorbent, this surface, if this is chemically active, chemically active means, say for example, an acidic pH. At acidic pH, this surface will have a lot of H plus protons, right? And if you want to remove some negative ions like say chromium Cr2O4, Cr2O7 2 minus. This is nothing, this is chromium 6. So what happened is this will get electrostatic attraction, correct? If negative is there, that means when the adsorbent itself is chemically active, the ions to be removed is another opposite charge, then this is binding due to electrostatic attraction. So what happened is, due to opposite charge, the ions get attracted onto the surface of the adsorbent itself and removed it. So this is called chemical adsorption. So the difference between these two is, in physical absorption is quite slow, not slow all the time, because it has to go into the pores, the micropore, the mesopore. Fine. For a chemical attraction, we know it is the formation of the chemical bonds. So it is quite fast. So this is the difference. Okay. Now let me come to real work of engineering streams. This is the basic fundamental of adsorption. Okay. Now you see here, first thing is, let me see whether still the camera is on. Now, firstly, what I mean to say is, let's say this is a reactor. Now I'm coming to the basic concept is over. I'm coming to the actual engineering problem, how we have to deal with the removal of heavy metals or any recalcitrant compounds using the adsorption theory. Okay, so let's say this is a reactor. It contains a lot of water. Okay, now we put some adsorbent over here. This is the adsorbent, and what happened is, you have lot of impurities here. You have a lot of impurities here, and this black is, I'll say, impurity, or what you want to remove, we call it adsorbent. Okay, now let me take some hypothetical conditions. Firstly, you see, CO is equal to initial concentration. Ce is equal to effluent, or we will say, I'll come to the point, equilibrium concentration. Now you see over here, by giving an example, let me say C0 and Ce. I'm not giving any questions. I'm just trying to make you understand this concept. So I'm using some hypothetical condition. Okay, let's say we are trying to remove something called, say, mercury. Mercury is very toxic. It's very toxic. Because of the mercury, the Minamata Bay disaster in 1952. Minamata Bay disaster due to mercury in 1950 to 1952 in Japan, due to mercury. All the aquatic life, fish got died, people got killed. Okay, so what happened is, in C0, let's say mercury is 10 milligram per liter. And let me put another condition over here. The dose is gram per liter. You are using 1 gram. When you use 1 gram of adsorbent, okay, the initial 10 it is reduced to say 6. Okay, that means I can say removable is 10 minus 6 is 4, so removable is 4. Am I correct? Now, by this condition, if you same initial concentration, if you use 2 gram, if 1 is taken out, if you use 2 gram, this is supposed to be, if 4 is removed, 2 is there, then this should be 8, correct? Because 1 is able to take out 4, so 2 should be able to have 8, and this should be 10 minus 8, this should be 2, correct? From this equation, we observe that 1 gram can absorb 4 milligram. So if you use 2 grams, we should be able to remove 8 milligram. So effluent should be 2, right? But actually, this is not the case that's happening. In practical life, we observe that it doesn't happen. So when 10 is there, when 2 gram is used, sometimes we observe that the effluent is not 2 but sometimes 4. So removal is 6 milligram per liter. That means it is not exactly linear. That means if I can do, or if I can drink 1 glass, 2% can drink 2 glass. That concept is not clear over here. Okay. Or if you are able to wash 5 clothes in 1 hour, in 2 hours you should be able to wash 10 clothes, right? That linear equation, it is not practicable over here. I'll tell you the reason. Then you think, sir, 4 milligram is removed here, 6 milligram is removed. So here, can I say the removal is 4 milligram is removed by 1 gram. But in this one, 6 milligram is removed by 2 gram. That is 3. Here it is 4. So you may take the average, you may try a new one, then in again 10, if you take say 4 grams, say simple 0.5 gram. For 0.5 gram, this is double. So 1 gram, half is 0.5. Since 4 is removed, it should be able to remove 2, right? That also doesn't happen. So sometimes, rather it is happening as sometimes 7. 7 means 3 is removed. That is 3 milligram is removed by 0.5. Therefore, per gram, it is 3 by 0.5 is equal to 6. So this is a concept with sometimes 6, sometimes 3, sometimes 4. Okay. I'm not doing anything that may be able to ask in the exams. I'm giving you the concept first. My point is, if you use double the concentration of the adsorbent dose, removal is not going to be linear. If you reduce the concentration by half, it's not going to be removed by half. It is not a linear equation. Okay. Why it is happening? Now I'm going to come into picture. Okay. Now you see properly over here, this figures, let's say this is the adsorbent, okay? This is the solution. This solution, we call it bulk solution. Okay. During the experiment, when you try to put adsorbent and shake it, what we find is there are a lot of impurities over here. These are all adsorbents. Okay, these are all adsorbent. This is the adsorbent. This is, look properly over here. What happened is, during the process, this particle is getting attached to this one. Okay. In the meantime, what happened is, sometimes some particle that is attached, it also comes down and remain here. Some particle also happens. That means, let me write over here, at an instant, there is always absorption and desorption. Desorption means this is a desorption, and this is absorption. So my point is, when you try to catch a fish, you haul it, you catch some fish got escape from your fingers, right? So constantly, some absorption is happening, some desorption also happens always. It is not that absorption is always there. Desorption also do happens. Number two, when absorption rate, the rate of the absorption is greater than rate of desorption. The net is, we call it adsorb. We call it adsorption, but actually it is only one way side. Okay, let me change my red color. It's getting diminished. Okay, now similarly, this side, number three, and rate of adsorption is equal to rate of desorption. So when the rate of the adsorption is equal to rate of the desorption, means 4 boys is getting inside the room, 4 boys is coming out. Then this condition is called equilibrium. So in a net, what we observe is no more absorption. Okay? Concept is clear? Firstly, there is always the rate of the adsorption is faster than the rate of the desorption. So what happens is the net is, when 10 is adsorbed, 2 will be escaped out. So the net is 8 is adsorbed. Okay. So then finally a time will come, the number of adsorption and the number of desorption is going to be constant. That place is called equilibrium, and at the time we will observe that there is no further more adsorption. That condition is called equilibrium, and that is the end of the experiment. Is that clear? Now the question comes is, how much particle is getting absorbed, how much is coming out? This is the thing we want to find out, right? What we came to know is, one very interesting point we observe, that is, let me ask you the question, what is the factor that makes absorption or equilibrium. What I mean to say is, what is the factor that makes the rate of adsorption very fast or the rate of the adsorption equal to the rate of the desorption? Rate of the desorption is same means equilibrium. Rate of adsorption is high means adsorption. What is the factor? Okay, fine. Now let me rub this part. Okay, what we observe from here is, look over here properly. One very interesting thing we obtain, that is, there is a functional relation between the adsorbate adsorb and adsorbate remain in bulk. Okay, so that means if there are a lot of ions over here lying, this is number of ions in bulk, and whatever adsorb here, these are number of ions adsorb. So between these two factors, there is a functional relationship we obtain. That's why we obtain that sometimes removal may be higher or may be lower with the increase in the dose. So some relation is lying between these two. Say for example, I'll tell you, if we have a lot of students outside the classroom and only one or two students is over here inside the classroom, definitely they'll be coming to push to attend the class. If the number of the students is already here too much, the number of the students outside is very little, then they may not be able to come inside because of the saturation of the adsorption, correct? So the relation is there. My point is, we are trying to identify how much student is there in the classroom and how much student outside. If outside is there, they have a driving force to come inside the classroom. If inside is more, the driving force to come inside will be very less. But what is that exact relation? Is it a linear relation? Already I have given you one example. It is not a linear relation. So one functional relationship we are trying to obtain. Okay, so there is a functional relationship between the adsorbent already adsorbed and in the bulk, and this relation is called isotherm. Okay, this relationship is called isotherm. So isotherm is nothing, it is the functional or the mathematical relation that exists between how much ion is there in the adsorb, and how much ions are left in the bulk solution or that is to be adsorbed. Okay, so this is called the isotherm equation. Isotherm. And isotherm, definitely it is nothing, it is a function of ions in bulk and adsorbent. Correct? We are trying to identify the mathematical functional relationship between these two. Okay? Fine. If you want to have a look, you can pause the video and you can grasp it. Okay? Now let me come to the isotherm. Okay? Now, now the question is, this isotherm, or in another way, it is called the mathematical matheme it's a mathematical equation. Okay, there are a lot of mathematical equation that is derived by many scientists. For the Mtech, derivation is not important, and the most commonly used isotherm are: number one, Langmuir isotherm. Okay, number two is Freundlich's isotherm. Now let me explain. So there was a scientist called Mr. Langmuir. He obtained an equation. Before that, let me give you one part. QE. QE is the amount of ions absorbed per gram of adsorbent. Amounts of ion absorbed means the initial concentration minus the final concentration. Okay? So divided by M into volume. I'll give you the explanation why we use the word volume. Okay. So C naught minus C means it is milligram per liter. I want to know amount of the ions absorbed means this is milligram per liter. If you multiply by the volume, this liter will be cancelled. So you will get how much milligram of the ions is absorbed per gram of the adsorbent. So answer will be milligram per gram. Okay. So QE, you have to remember, it is the amount of the ions absorbed per gram of the ions, gram of the adsorbent. Clear? So now let me describe about Langmuir isotherm and Freundlich's isotherm. Okay. So let me rub it off. You can have a look. Before describing this, let me see. What Langmuir says is, what this equation is, QE is equal to ABCE divided by 1 plus BCE. Look here, QE already I have given. A and B are Langmuir constant. Okay, I'll come to the point. A is also called monolayer coverage. Unit is milligram per gram. B is enthalpy constant. Just remember, okay. And CE is, we know, it is an equilibrium concentration. Now, this equation is nothing. This equation is QE is equal to F of CE. Am I correct? QE is a function of C. The relation between the equilibrium concentration means how much ion is left in a solution, in the bulk. QE, how much ion is already absorbed. Am I correct? So let me repeat it again. C means equilibrium concentration, how much ions are left into the solution. QE means how much ion is already absorbed per gram of the adsorbent. So we are trying to find this functional relationship. Okay. From this one, this is non-linear. We are trying to make it linearized. Okay. So from here, what we can see is 1 by QE is equal to 1 plus B C divided by A into B into CE. Correct? Implies to 1 by QE is equal to 1 by AB C plus 1 by A. Okay, you can say is 1 by QE, 1 by AB, 1 by CE plus 1 by A. Please look. Okay, so this two equation, this is going to be Y is equal to mx plus C. So Y is going to be 1 by QE, X is going to be 1 by C, and then M slope is 1 by AB, and intercept is 1 by A. Okay? And then, since intercept is equal to 1 by A, I can say A is equal to 1 by intercept. This is number 1. From this equation, we can find A is 1 by. The constant can be evaluated. So, the monolayer coverage is the 1 by intercept of this equation. Okay? What about B? We know that slope is equal to 1 by AB. So, slope is equal to 1 by A is already intercept. Intercept by B. Therefore, B is equal to intercept by slope. Is it clear? From this we can find. You don't worry for this. We are going to do a lot of numericals. Then you will grasp the point. Okay? So, after doing the experiment, we will find out the value of AB, and then we can predict for any other thing. Or let me give you one example. The application of this. So you copy down this one, fine. Why I am doing this, you may be getting confused. So let me explain you first over here. Say you have an industry. You have an industry. Your effluent concentration, your industry effluent. Effluent means that's going to be initial concentration. CO of say cadmium. You have a lot of cadmium or copper. Your is electropathy industry. It's coming around 120 milligram per liter. Fine. Now you say it's around 120 milligram per liter, and you said the discharge is 0.01 mld. It's very, very low. 0.01 mld means this is a discharge. So you are going to say, sir, tell me if I purchase, actually some noise is coming, let me give it a try. So my point is, if you are using a commercial activated carbon you purchase from the market, then how much you have to use? How much you have to use, correct? But you cannot test an experiment at 120 milligram per liter. It's very huge. And how much you can design it. This is completely effluent treatment plant. Right. So what you will do is in the lab, inside your lab, in the lab, what you'll do is you'll do some experiments. Simple. Say you can do C naught is equal to say 5, 10, 15, very small. Those. Adsorbent also, activated carbon also you can use with 0.5, 0.5, very little. You are going to use very little, very economical. From this experiment, you are going to find what is your CE value, correct? If you are doing experiment with 5, what will be the CE value? So CE you will obtain. If you obtain CE, you can find QE also. QE is equal to C naught minus CE divided by M into volume. Already you have your dose, this is M, correct? So then you will have your 1 by C, you can calculate by yourself. You can have your 1 by QE, okay, and then you can obtain a new A and B, okay. So your Y is equal to mx plus C, you will obtain it using this equation for 120 milligram C naught. If C naught is equal to 120 milligram per liter, if you want the C to be permissible limit of 0.5 milligram per liter, how much M you have to, and volume is nothing, your discharge, okay, how much dose you have to use can be evaluated. Let me come back again. Listen here properly. In the lab, you will do some experiment. You will do initial concentration with 5, 10, 15. Yours is 120. You dilute it with the water and you can make different concentration. Dose, don't use much adsorbent dose. Use only little 0.5, very economical. By doing the experiment, you will find how much adsorbent occurs. So from 5, how much is reduced, you will get it. Effluent concentration, correct? So if you got this, you can estimate what is QE value very easily. If you know QE, the reciprocal of 1 by C or 1 by Q, you can obtain it. And you can use this equation. You can find A and B. Once you find A and B equation, you can obtain a new equation, Y is equal to mx plus C. The equation for activated carbon to remove cadmium or copper from your industry. So, and this equation is not true for all the conditions. It is for a particular adsorbent and a particular adsorbent of a certain environment. So, if the cadmium or the copper is in a drinking water, that's different. If the copper and the cadmium is in some other different wastewater, it will be different, because they will have different other impurities and they have an impact. So by obtaining this relation, if you say this one, your 120 milligram will be here. Effluent, how much you want, you may say 0.5 milligram per liter. Volume means almost your discharge. So how much M, how much activated carbon is required, you can estimate. That's why we have to do some small experiment in the lab. We have to identify the minimum functional relationship between this, obtain it for larger scale, and then solve the problem. Okay? So if you solve one problem, it will be easy, which will be my next presentation. So let me again write it here. Okay, so now let me rewrite the steps again. The step is number one, any industry is there. Industry treatment design. What we'll do is first experiment in the lab between number one, adsorbent, and number two, adsorbent, which you are going to use, right? Number B, obtain the functional relation, or we call it isotherms. Okay. Number C, using the equation, predict for actual industrial concentration and find the dose of adsorbent required. Okay, fine. This is the way we are going to do it. Next class we'll solve one problem. But before that, for the friend link, let me do it. For the friend link equation, what it said is QE is equal to KF C to the power 1 by N. This is friend link equation. Friend link is derived from different point of view. I'll come back to that. But this is a non-linear equation. To linearize, what we do is log of QE is equal to log of KF plus 1 by N log of C. So in this equation, this one is Y, this one is the C, or we call it intercept, correct? And log C is X, and 1 by N is the slope. So N is equal to slope, N is equal to 1 by slope. And what about the intercept? Intercept is KF. So KF is equal to e to the power intercept. Okay, this is the way we find the Langmuir and the Franklin equation. In next class, I'll solve the problem. Okay, now let me do the difference in relationship between the Langmuir and the Franklin. Okay, Langmuir versus Franklin. Okay, number one, Langmuir assumes that it's monolayer coverage. Number two, all ions absorb doesn't interact with each other. And the surface is homogeneous. Okay. The meaning is, if say this is the adsorbent, if this is the adsorbent, number one, if any ions are coming to bind, if any ions are coming to bind, they will bind here. They will bind on the surface. They will bind on the surface, and they will make a, this is called monolayer. That means the particle, one may be attacking here. If this is empty, he won't go on top of this one. This won't be happen. So every ions will form a layer. And this is homogeneous. Means the surface property are same. And all the ions means, say here, this is one ion. This is one chloride. This is another chloride. The meaning is these two ions will not interact to each other. Say for example, my body is there, one mosquito, another mosquito, everything is attacking. The meaning is the two mosquitoes that is on my surface, they will not interact to each other. Very simple logic is there, besides chloride. Say some ions like here, say copper may be attached. Not only chloride, copper also. The meaning is this copper and chloride will not react. The chloride is attaching onto the surface because of the adsorbent. Copper is because of the adsorbent. But these two will not combine. So if it is combined, then it may not be homogeneous. It may not be a monolayer coverage. So to define this monolayer coverage, they are saying that it does not interact with each other. Okay? So based on all these assumptions, Langmuir have identified that equation. For the Freundlich, what it said is the surface is heterogeneous. Heterogeneous. Okay? Means it is not homogeneous. And another one is adsorption is exponential. That means the rate of adsorption is going to jump. The rate of adsorption is increased exponentially. It is not gradually. So it doesn't mean that all the adsorption is completely Freundlich or all is Langmuir. What we will do is our adsorption data will be checked on two these isotherms. The isotherm that gives better results, we will say that okay, so finally the activated carbon for copper removal is monolayer, is homogeneous, surface is homogeneous. Then we will explain it. And Langmuir's A monolayer means the total surface. Okay, there is milligram, how much milligram of the ions in a monolayer per gram. On other way, this is also called maximum adsorption capacity. Obviously, sometimes we call it Q max because since only monolayer coverage is going to form, no double layer will be there. The maximum monolayer coverage, there is a maximum adsorption capacity itself, right? So look here properly. Next class, I'll continue with the numericals of this. Okay? Thank you.